Hey, this is Lab Group 2A. I'm David, and I was the technician for this lab. And this is Lab 8, Optical Testing with Shear Plate Interferometry. So for the first part of the lab, we basically utilize Table B. As always, we have our laser and spatial filter with microscope and the objective lens. The key feature of this table was the collimating lens, in which there were two translation axes that were really important. One parallel to the rail and one perpendicular to the rail, which we'll get to later. And then we have a non-wedge shear plate, something a little different. And instead of seeing the fringes on top of the plastic thing that we're used to, we were able to project them on a viewing screen such as this. Because they were kind of intense when trying to take pictures, since pictures were a pretty big part of this lab, we also used two polarizers to decrease the intensity of the beam. So our test lens was a plano-convex lens, and this is kind of important because we want to introduce spherical aberration on the fringes we see up here. So instead of using a doublet for the typical beam expander, that's why we use this lens. It should be mentioned that the translation axis parallel to the rail is for defocus, and the other one is for decentering. Tilt was not utilized in this part. So for the latter half of the lab, we were at Table A. Basically the same setup. We have the laser, the spatial filter, but this time instead of a plano-convex lens, we have a doublet. This ensures that we have low spherical aberration. Goes through a mirror, and then we go to a wedge shear plate instead of the non-wedge. And we'll talk about that later on. There were two parts to this lab. One was testing the mirror. We used defocus and tilt for that. And another reference lens was used, which was also a doublet, also ensuring no spherical aberration, which you'll see in our results. For the last part, we used a test lens. And again, we went to defocus and decenter to see changes in the fringes. And we also did see spherical aberration since this is not a doublet. So for the first part on Table A, we had the mirror and the reference lens. Because this is doublet, we basically want to make sure that there's no effect coming off this reference lens, hence only the mirror is used when tilting and defocusing to get the effect we want. Basically, we want to find best focus, and how do we do that? We basically look at the fringes. Right now you can see that it is because it's along that reference line on the shear plate. But to find that easily, we basically look for the BFL off the reference lens and try to find the smallest point on the mirror, which is probably very hard to see through the camera. So here's a quick look at defocus. As you can see, as more defocus is added, the amount of fringes increases tenfold. Basically, best focus is usually defined by seeing the least amount of fringes. That's also another easy way to find it. By adding tilt, though, a different effect was seen as the fringes were displaced, but the space between them hasn't really changed. For all three settings, there's XYZ tilt on the mirror given. Go.
Hi, I'm Brian, and I was layout and photographer. Alright, so we're going to start with part A, some of the images we took, and continue to part D. And what we have here is, this is just the best focus. You can see one fringe here. That was the best we could get. It's a little light on this photo, but it was much clearer with our own eyes. Alright, so our next photo that we took was defocus here. And so you can see the fringes. We have multiple fringes now. And then you can see when we added tilt to the system, there's this area of without fringes, and then we have this area with fringes. It just looks basically the same. And then our next image here is when we have defocus and decentering. And so you can see we have some curved elements here. And our next image here is we rotated the lens around 180 degrees, inducing more aberrations into the system. So you can see when we decenter the system, we have curved aberrations here showing up. And we'll talk more about these might be later. And then you can see here when we add defocus to the system as well. This is what it looks like.
Hi, my name is Steven, and I was the scribe. So we used two different shear plates in this lab, and we're going to try to explain why. Well, for this shear plate, it's harder to get collimation because essentially there's no wedge, therefore there's no OPD difference as a function of pupil. This means the way we detect collimation will be a uniform beam. On here, we have a wedge shear plate, which is easier to detect collimation because as a function of pupil, we have a linearly changing OPD, which will give us horizontal fringes. So this is more sensitive to collimation, but it's harder to actually detect aberrations with this. With this one, we were just easier. It was easier from our results. We determined that it was easier from our results to detect aberrations using the non-wedge shear plate. So for this, I'm going to just sort of explain how we analyze an interferogram. We have an interferogram here, say, and we count the fringes over the pupil. Keep in mind this is this is a positive and sort of there's a negative, so you go 1, 2, 3, 3, 2, 1, and then so you graph it and you get a fourth order polynomial fit, and you take the coefficients from your polynomial and you use these equations to find each of the aberrations inside. Delta is your normalized shear something. Brian, what is it?
It's the shear distance normalized by the pupil radius.
There you go. There you have it. Guest star Brian. So there you go.